So to speed this up just a little bit, I'm going to convert things into megatons here for a bit. 1 megaton is equivalent to 4.18 times 10 to the 15th joules. We're gonna allow for right now that an A-bomb might have an energy equivalent of about 1/10 of a megaton, and a hydrogen bomb could run up to about 25 megatons. Okay. So now we just need to do a little bit of math, basically dividing this number by that number, and we'll know what we need in megatons. 3.74 times 10 to the 23rd. Oops, this is kilojoules, and I wrote 23 when I meant 25. It happens. 25, but then we have to add 3 more, because it was kilojoules. So 3.74 times 10 to the 28th joules divided by 4.18 times 10 to the 15th joules per megaton. It's going to give us a little quick action on the calculator. Okay, ready for this? This is going to give us 8.95 times 10 to the 12th megatons. It's roughly 9 trillion megatons. In terms of A-bombs, that's 90 trillion A-bombs. And in terms of hydrogen bombs, give me one sec. It's going to work out to 360 times 10 to the 9th hydrogen bombs. I'll double check that in a second, but that's right. 360 billion hydrogen bombs. So roughly in the neighborhood of 60 hydrogen bombs for every man, woman, and child on the face of the earth as of about the year 2000. The total actual number of hydrogen bombs on the face of the earth, I didn't actually look up, but it's substantially less than 10 to the 5th, thank God. So we would need something like 360 times 10 to the 4th, which is, hang on a second here, 360 times 10 to the 4th, which is the decimal place over 3.6 times 10 to the 6th. We would need something like 3 million times as many hydrogen bombs as actually exist on this planet. So I'll look up the total energy output of a typical fission nuclear reactor in a year and put it in there as well, but it's going to be something on this same order. So remembering this 3 to 4 million, that's not how many hydrogen bombs we need or how many reactors we need. That's how many times the total number that exists on the Earth that we need. We need actually 360 billion hydrogen bombs and that's just to basically melt the core of Mars. I didn't take into account how much energy we'd have to put into it to just bring it up to the temperature of melting. Since it won't, due to the laws of thermodynamics, it won't actually melt until we brought it up to the temperature at which it would melt. I don't know what its current temperature is, but substantially below its melting point. Or even if it were right at its melting point right now, but just a little enough below it to have turned solid, it would still take 360 billion hydrogen bombs to cause it to melt, because it takes extra energy to undergo that phase transition. We can play around with the numbers some. We could try only melting like 1/10 of the core of Mars, in which case we're only talking about 36 billion hydrogen bombs. Major point of this is to illustrate that, a hydrogen bomb is a big thing, and the core of Mars is a big thing, but not all big numbers are created equal. The core of Mars is about 9 or 10 or 11 orders of magnitude bigger than the hydrogen bomb. Hydrogen bombs are big. Mars is about 1 trillion times bigger. Again, one of those things you run into with numbers, you can just keep going up and up and up. There is no limit to how far up you can go when it comes to numbers.